Hey everyone, in this video we're going to be talking about Newton's method. Newton's method is an open root finding method for nonlinear functions, meaning that we pick an initial x value and then we iteratively solve for our root from that point. Newton's method uses Taylor's series expansion, which, if you're unfamiliar, is just a method for us to recreate any continuous function as a polynomial, which is great as the derivatives of polynomials are simple, which will be beneficial to us here shortly. In this video, we will not be solving an actual problem. This video is just meant for the theory and the steps behind Newton's method. In the next video, we will solve a problem using Newton's method in numerous ways, such as by hand and in several programming languages. So let's just get right into the procedure for Newton's method. Firstly, just like any other open root finding method, we must start with an initial guess of our root. So we take a guess at the x input on which we think our root might lie. Then we'll create a first order Taylor series expansion at that x value guess. So a first order Taylor series approximation looks like this. So it is basically saying if we begin at this point here, that being our original guess, then we can find the derivative, which tells us the instantaneous rate of change of our function for this input. Then this final term here is just telling us the size of step that we take along our derivative. In step 3 of the Newton method, we need to find the point at which our tangent from the derivative hits the x-axis. Therefore, we can set our previously found function to 0 and we can simply solve for the input that gives us an output of 0. Now, we can actually find this term for a tangent. So, I'm saying we'll find a general function to find the x-axis for any function where the output is 0. Beginning with our first order Taylor series approximation, we set our output to 0. Then, expanding our derivative and the step terms, we can isolate our function for the input that gives us an output of 0. So, doing so results in the equation which is the base of Newton's method. So, if you've seen this equation before and didn't know where it came from, well, now you know. Now that we have solved for the input that gives our tangent an output of 0, we plug this input into our function and find the output for our next iteration in Newton's method. Then we just continue our process until we reach an acceptable amount of error. That is, when our approximated x value is close enough to our actual x value. So, we should also talk about what Newton's method excels at, and what can cause Newton's method to fail. Newton's method is very fast at finding some roots, much faster than the closed root finding methods that we talked about previously. However, there is no guarantee that Newton's method won't diverge. To illustrate this, imagine if we had a step function, or even a function similar to a step function. In a proper step function, Newton's method will never work, which should make sense because we cannot draw a tangent line on any of these inputs that'll cross the x-axis. Even in a more fluent function here, it is clear that some inputs will send us very, very far from our true answer. These are just a few things to consider and look for as we begin performing and solving more examples using the Newton's method in the coming videos. Hey everyone, in this video we're going to be walking through and solving an example using Newton's method by hand. As we went through in the previous video, Newton's method is an open root finding method for nonlinear functions, meaning that we pick an initial x value and then iteratively solve for our root from that point. I will leave a link to the video on the theory and procedure for Newton's method in the description below for anyone that is interested. Alright, so we are told to solve for the rightmost root of the function here, f of x is equal to x squared minus 2, through 3 iterations of Newton's method. So, the function that we are given is just a parabola that is shifted in the negative y direction. Our first step in Newton's method is that we must choose an initial input guess value. So let's just use 2. So our goal right now is to find where the tangent line of our initial x guess crosses the x-axis. As we talked about in the previous video, this is approximated by our first order Taylor series expansion. So this is found using the following equation which we derived in that previous video. What this equation is saying is that to find our next guess, our next iteration of x, we just take our current x value minus our evaluated function at our current x value over the derivative of our function evaluated at the current x value. So we can first evaluate our function for our initial x guess. This is equal to 2. And as you can see from the equation, we also need to know the derivative of our function. The derivative of x squared minus 2 is simply 2x. So evaluating this function at our current x value gives 4. All we have to do here is plug in our values, and we receive our next input for x, which is 1.5. So that means following this tangent line here, we cross the x-axis at 1.5. And that is all we need to do for the first iteration. Moving forward, we just need to continue repeating this procedure that we just did. So all we have to do is evaluate our function and the derivative at 1.5. Then we can find the next value of x. The approximate root at our second iteration here is equal to 1.416. Lastly, we just need to complete one more iteration of Newton's method, using our third x value, which is 1.416. Let's just evaluate our function and the derivative at 1.416. This gives us 1.414, which is really close to the real root of this function, which is great. So, as you can see here, this method of root solving is quite a bit faster than many of the closed root finding methods that we examined previously. You could continue to perform iterations, and as long as Newton's method is converging, like in this example, then your solution will continually become more accurate. Hey everyone, in this video we're going to be walking through how to solve for a root of a nonlinear equation using the Newton's method in Python. As we went through in a previous video, Newton's method is an open root finding method for nonlinear functions, meaning that we pick an initial x value and then we iteratively solve for our root from that point. I will leave a link to a video on the full theory and procedure for Newton's method in the description down below, but let's go through a quick review of what Newton's method is. Let's say that we have a function that looks like this, and we are trying to find where this nonlinear equation crosses the x-axis. Well, we must first start with an initial guess as to where we think the intersection point might be. So let's say it's here at x. Well, using our function, its derivative, and our initial guess in the following formula, we can work our way iteratively towards the x-intercept. So we get an x value, find the derivative at that point, which is telling us how quickly the slope is changing at that one specific point, the evaluated function at that point, and then we essentially take a step down from the derivative slope, find our new x value, and continue the process. So after that quick review, let's talk about creating our Newton's method Python function. We're going to set this up as a Python function, as this will give us some flexibility to use this code again in the future for any function that we want to solve using Newton's method. To define our Newton's method function, we need to type def and then give it a name. So let's just keep it simple here and call it Newton's method. Then we're going to have 4 parameters, meaning our user will have to give us 4 arguments to satisfy those 4 parameters. So we will need 4 inputs, that is the 4 arguments, from our user to actually run this function. Let's first ask for the user's function, the func, and the user will input this as a string. Then we need the derivative of the function from the user to find the next step in Newton's method. So let's just call this funcDeriv. Then we need our user's initial guess, that is the initial starting point from which we'll begin solving for the root of the function. Then we need to know how many iterations the user wants us to run. The more iterations we have, the longer the program will run for, and the more accurate our answer will be should we have a converging solution. To interpret the 2 strings, the func and the funcDeriv, that our user entered as a usable mathematical function, we need to create 2 functions that will evaluate our function for a given input, and this can be done like so. This Python eval method here is what we can use to turn our user's entered string function to something that Python can read as a proper mathematical function. So, anytime in our code we put f of x, the number we put into the brackets for x will be evaluated using this Python function here, which in turn will solve our function with the input value. So we can just repeat this function again to interpret the string our user enters for the function's derivative. Now, let's just create our simple for loop, which will be our iterative numerical solver. We save for an intercept in range, and then we will say 1 to n, where n is the number of iterations that our user wanted. So our for loop will loop iteratively from 1 all the way up to n. Now we must enter our Newton's method formula, which we discussed earlier. I'm going to just use I for our next iteration variable and x as our current iteration variable. So we type that for our next iterations variable, x value, is going to equal our current iteration's x guess minus the function evaluated at the current x value divided by the derivative of the function evaluated at the current x value. Then, to update our current x value, we must say that our current x value is going to equal our next x value. So it takes on its value. And that is really all we need to do to begin solving problems using Newton's method in Python. As an example, let's say that we are told to solve for the 2 roots of x squared minus 2. As we can only solve for one root at a time, let's begin by solving for our rightmost root. And to do this, we first need to call our function. To call a Python function, we just need to type the name of the function, so Newton's method. Then we need to give it the arguments for this given function. So we'll enter our function of interest as a string, enter the derivative of our function as a string, our initial guess of x, and how many iterations we want this to run for. Then let's just copy and paste this function call and change our initial guess somewhere much lower. If you have a function and you are unsure of a good initial guess, it is always a good idea to first graph the function and then make a guess based on that. Then, when we run our function, we will receive the following information. And if we head over to desmos.com and actually graph our function, we can see that we do land on the same roots. So there we go, we have just implemented Newton's method into Python. Although this may not be the most efficient possible way to code Newton's method in Python, I hope that it helped you and maybe taught you something along the way. Hey everyone, in this video we're going to be walking through how to solve for a root of a nonlinear equation using Newton's method in Microsoft Excel. As we went through in the previous video, Newton's method is an open root finding method for nonlinear functions, meaning that we pick an initial x value and then we iteratively solve for our root from that point. I will leave a link in the description below on the theory and procedure for Newton's method in the description. Alright, so we are told to solve for the rightmost root of this function here. F of x is equal to x squared minus 2 through 10 iterations of Newton's method. So, Newton's method in Excel is relatively easy to implement. The first thing that we can do in Newton's method is simply evaluate the derivative of our function, which I've already done here, and you can see this in the top right corner. Now, let's create 4 headers here. Let's call our first column iteration, and this will just be an easy way to quickly tell us which iteration we are currently on. Secondly, let's add x, current. This is going to be our current x value guess at this iteration. In our third column, let's evaluate our function at the current x value. Be sure to select the current x value cell for all of your inputs to x within your function. This will ensure that your formula works as we increase our iterations here shortly. In the next and final column, we just need to repeat the previous evaluation step, except now we are using the derivative of our function of interest. So let's just do that now. Alright, so now we can fill in this row here using our initial x guess. Let's just use 2. So we put that in our initial iteration 0 current value of x. And as you can see here, the rest of the columns update with that input. Now, to find our next value of x, we need to use the following formula, which was derived in our Newton's method theory and procedure video. The idea here is that we use a first order Taylor series expansion to find where our tangent line crosses the x-axis. So, as this newly found x term is replacing our previous iteration's x value guess, we can put this in iteration 1's current x value. Now what we need to do is drag down these few columns, and we can validate that our answer is not diverging, meaning that we can see that our current x value is trending towards very similar values, and it is not running away from itself. If these numbers were getting significantly larger or changing in different ways, then we could probably assume that our function is diverging, which means we will never get to a proper answer, and we need a better starting guess. As you can see here, our answer is actually converging quickly and very well. If your answer is diverging, I highly recommend that you plot your function of interest and choose a better starting guess. However, this will not fix everything, as certain functions, like a step function, cannot be used in Newton's method, like we discussed in the previous theory video. Hey everyone, in this video, we're going to walk through how to solve for the root of a nonlinear equation using Newton's method in Google Sheets. As we went through in a previous video, Newton's method is an open root finding method for nonlinear functions, meaning that we pick an initial x value and then we iteratively solve for our root from that point. I will leave a link to the theory video on Newton's method in the description below. Alright, so we are told to solve for the rightmost root of the function f of x is equal to x squared minus 2 through 10 iterations of Newton's method. So, Newton's method in Google Sheets is relatively easy to implement. The first thing we can do in Newton's method is simply evaluate the derivative of a function, which I have already done here, and you can see that in the top right corner. Now, let's create 4 headers here. Let's call our first column iteration, and this will just be an easy way of quickly tracking our iteration that we are currently on. Secondly, let's add x, current. This is going to be our x value guess at this iteration. In our third column, let's evaluate our function using the current value of x. Be sure to select the current x value cell for all inputs of x into your function to ensure this formula works as we increase our iterations here shortly. In the next column, we just need to repeat the previous evaluation step, except now we are using the derivative of our function of interest. So let's just do that now. We can now fill in this row using our initial x guess value. Let's just use 2. So we put that in our initial iteration 0 current guess. And as you can see, the rest of the columns update with that input. Now, to find our next value of x, we need to use the following formula, which is derived in our Newton's method theory and procedure video that I talked about previously. The idea here is that we can use this first order Taylor series expansion to find the x value at which our tangent crosses the x-axis. So, as this newly found x term is replacing our previous iteration's x value guess, we can put this in iteration 1's current x value. Now, all we need to do is drag down a few rows and columns and we can validate that our answer is not diverging. Meaning, we can see our current x values trend towards very similar values, and they are not running away from each other. As we want, we can see here that our answer is converging very quickly and very well. If your answer is diverging, I highly recommend that you plot your function of interest and choose a better starting guess. However, this will not fix everything, as certain functions, like a step function, cannot be used in Newton's method, like we discussed in the previous theory video. Thank you for checking out this video, and I hope it helped your understanding of how we can implement Newton's method into Google Sheets. If you enjoyed, please like, subscribe, and consider checking out our YouTube memberships or our Patreon page down below. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.